We could also talk about bases as being weak or strong. And previously we had said that a strong base, right, is going to be one that dissociates completely. We did have a list of strong bases to memorize, and all of them had hydroxide ions in them. So I'm going to use M here as just a generic metal cation and then a hydroxide ion. And when we put that in water, it's going to separate into my cation plus hydroxide ions. Note I am drawing an arrow just in one direction. So again, these are not reversible. We are not going to establish equilibrium. I'm not going to have an equilibrium constant that defines the strength of a strong base, right? They're completely dissociated. If I was to draw a beaker, I would have my cation, my hydroxide ions, and then some water in there, right? I'm not going to have any of my associated ions, right? They're all dissociated. Weak bases, these guys are going to dissociate partially. If you want to think Bronsted-Lowry, some of them are going to accept protons, some of them aren't, right? Partially. I'm just going to use a generic B for base here. I'm going to react it with water. And I'm going to produce hydroxide ions. So this is going to be my conjugate base. And then my conjugate acid, right? We're going to add a proton to my base. Remember, bases are proton acceptors. So B is going to take a proton from water to produce my conjugate base, hydroxide ions, and then my conjugate acid, BH+. So this is my conjugate acid. It is acidic. It can donate a proton, right? And go back in the opposite direction. I do have arrows going in both directions. So my base B can take a proton from water, and then my conjugate acid BH+ can donate that proton back to hydroxide ions to produce my unprotonated original base and water again. So this is acidic, right? It can donate H+. I don't really think of having a conjugate acid when I look at a strong base, right? I do have M+. If you want to kind of think of that as the equivalent to my conjugate acid, I mean, it's not really. It's going to be inert. We can actually write that there if we wanted inert. So if I have sodium hydroxide, it's going to separate into sodium ions and hydroxide ions. Sodium ions are not going to do anything. They're going to be spectator ions. We'll write net ionic equations for these later on, and they're just going to get canceled out. If we were to do our beaker drawing for our weak base, I do have my hydroxide ions, I do have my conjugate acid, plus I have my base, and then we could throw some water in there. And then just like we did with our weak acids, our products do exist in a small amount, usually around 5% again. So we can write equilibrium constant expressions for these. I'm going to call it Kb this time, and our values are generally going to be small, right? Because they exist at equilibrium, we can write our expression. This time I'm going to put a subscript B for base. It's going to be my concentration of my products over the concentration of my reactants. Again, we're excluding water. These are all at equilibrium, and as usual, I didn't leave myself enough room. And again, they're going to be relatively small values, right? Most of what's in my beaker there, if we wanted to, again, not to scale, but I could add a few more B's in there for base. Calculating pH, if it's a strong base, it's pretty straightforward. our strong bases that you learned, some of them did have one cation per hydroxide ion. Some of them I'm going to have 2 hydroxide ions per cation because that cation likes to lose 2 electrons, or that atom likes to lose 2 electrons when it forms a cation. So kind of 2 different ways here. If I just have MOH, right? If that's the case, then my strong base, SB for strong base concentration, is going to be equal to my hydroxide ion concentration, right? If I go up and I look, that's the case I had here, right? If I have coefficients of 1 here, so for every 1 MOH, I have 1 OH. So if this was 0.500 molar, then this is also 0.500 molar, right? It's a 1-to-1 ratio. And because my arrow is only going in this one direction, every bit I have here is over there, right? When the reaction's done, I have no MOH, right? If I look at my beaker here, it's all M plus and OH minus. So in that case, whatever my strong base concentration is my hydroxide ion concentration. The other instance is if I have 2 hydroxide ions, right? Something like this, we can write an example. If I had calcium hydroxide, that is also going to dissociate completely, but I'm going to have 2 hydroxide ions for every 1 calcium hydroxide in this case. So in this case, right, using numbers again, if this was 0.500 molar, this is actually going to be 1.00 molar, right? I have twice as much. So in this case, whatever the concentration of my strong base is, I need to multiply that by 2, and then that's going to give me my concentration of hydroxide ions, right? If I had 0.200 molar of this, because it's a 1-to-2 ratio, I'm going to have to multiply that by 2 to get my concentration of hydroxide ions. And then once you have that, remember pH is the negative log of our hydronium ion concentration, not hydroxide ion concentration. So this is one that you could do 2 different ways, right? We could figure out our POH. That's the negative log of my hydroxide ion concentration. And then we could subtract that number from 14 because my POH plus my pH is equal to 14. The other way is you could take your hydroxide ion concentration, divide it into kW, right? 1.0 times 10 to the negative 14th is equal to hydronium ion concentration multiplied by hydroxide ion concentration. So if we divide our hydroxide ion concentration into kW, I get the hydronium ion concentration, and then we can take the negative log of that value. Both of those methods will get us our pH. So again, if there's one, right, cation for every 1 hydroxide, my strong base concentration and my hydroxide ion concentration are going to be the same value. If I have 2 hydroxide for every 1 metal cation, I need to take my strong base concentration and multiply it by 2 to get my hydroxide ion concentration. To calculate the pH of a weak base, here we're going to need an ice table again, just like we did with our weak acids, right? It's not completely dissociated, or it hasn't accepted all of the protons, if we want to think about it that way, right? It's going in that direction, but it's also going in this direction. So if I had 2 molar of this, I don't necessarily have 2 molar of this, right? It's not completely in that direction. So we're going to calculate, and let's just jump into example. The steps are going to be very similar to what we did with weak acids. We're going to write what's called our base dissociation equilibrium equation. We're going to write our Kb expression, we're going to set up an ice table. We're going to solve for X. This time X is going to be hydroxide ions, however. And then from there, we'll figure out our pH. So let's just jump into an example. I think it's kind of easier to just go through it. So we're going to calculate the pH. Of a 0.100 molar ammonia solution. And the Kb of ammonia is 1.8 times 10 to the negative fifth. So the first thing I'm going to do, and I didn't write the name of it down, so we'll do that here, but we're going to write the base dissociation equilibrium equation. So when we wrote our acid dissociation equilibrium equation, it was the reaction of the acid plus water. Our base dissociation equilibrium equation is going to be the reaction of our base plus water. So my base in this case is ammonia. I'm going to react it with water, which is a pure liquid. And then remember, bases are going to accept a proton. So NH3 is going to become NH4 plus, so ammonium ions. Water is acting like the acid in this case. It has lost a proton, so I'm going to have hydroxide ions. So my base, water is acting like an acid. This is my conjugate acid, which is actually acidic, right? It can give that proton back to hydroxide ions, going back in this direction to form ammonia and water. And then hydroxide ions is my conjugate base. From here, we'll make our ice table. So my initial concentrations, my change, and my equilibrium concentrations. My initial concentration is given to us in the problem. We're not going to care about water. It's a pure liquid. I haven't wrote the expression yet, but it's not going to be part of it. And initially, I don't have any product. We're going to lose some amount. We don't know what it is. We'll call it X. We gain on the product side. I have coefficients of 1 in front of all of those, so 1x for all of them. And then at equilibrium, what I started out with minus what I lost. 0 plus x, right? What we started out with plus what we gained, and then the same here. I'm going to write my equilibrium constant expression. So Kb, which is equal to 1.8 times 10 to the negative fifth, is going to be equal to the concentration of ammonium ions multiplied by the concentration of hydroxide ions. That's supposed to be a plus sign, it just got really messy. Over the concentration of ammonia. And again, we're leaving water out. It's a pure liquid. It's not part of my expression. So plugging those in, I have x times x, or x squared, over 0.100 minus x. And then our Kb is small, right? It is less than 10 to the negative third, so we can use that assumption. We're going to assume that 0.100 minus x is about equal to 0.100. This is, of course, more accurate the more concentrated your base is initially, but usually it will work for us, right? We could do that little test if we're unsure. So I'm going to rewrite that one more time just so I have it a little neater. 1.8 times 10 to the negative fifth is going to equal x squared, and then using my assumption is just over 0.100. So I'm going to grab my calculator. I want you guys to do the same, and we'll solve for x here. And I got 0.0013, and I am going to double check my work. So I'm just typing it in again. And I got the same answer. So we're not done, right? The problem asks us to calculate the pH, and I'm actually going to have us calculate all of the concentrations at equilibrium also, because that'll help us get a handle on how we're going to do pH, right? So at equilibrium, my ammonia concentration is going to be 0.100 minus X. Ammonium is going to be X, and then hydroxide is also going to be X. So ammonia 0.100 minus 0.0013. Ammonium, I will do that math here in a minute. Hydroxide, also equal to X. And I got 0.099 molar. So again, watch out for significant digits when you're doing that subtraction. So 3 after the decimal point, 4 after the decimal point. I do want 3 after the decimal point. So I get 0.0987. That's 7 rounds at 8 up to a 9. So back up to pH, right? Remember, pH is the negative log of my hydronium ion concentration. When I'm doing this with weak acids, X is my hydronium ion concentration. When I'm calculating it with a weak base, X is actually my hydroxide ion concentration. So we can go back up to this little list of things that we know to calculate our pH. So I can use this to determine hydronium ion concentration and then get the pH using this expression. Or I can calculate my pOH and then subtract it from 14. Either way works. I'm going to actually calculate hydronium ion concentration just for practice. So if I want my concentration of hydronium ions, I know that hydronium ions multiplied by hydroxide ions anytime I have an aqueous solution is always going to be equal to Kw, which is 1.0 times 10 to the negative 14th. So if I divide 0.0013 into Kw, we will get hydronium ion concentration. So I'm typing into my calculator right now. And I get 7.7 times 10 to the negative 12th molar. So pH, then I can just take the negative log of that value. That's a 12. So getting my calculator again. Do make sure you're using log base 10. In chapter 12, we use natural logs. So you might be in the habit of hitting that button. We don't want to use that one this time, right? We want the LOG version. So I get 11.11 for my pH. So significant digits, again, we have that new rule. This is 2 significant digits. My pH is a log value, so only the digits after the decimal point are going to count. So that first 11 doesn't count. So the 0.11 that comes after my decimal point are my 2 significant digits. Just real quick, if you wanted to do it the other way, let me just grab a different color. If I wanted to do my pOH, I'm going to take the negative log of 0.0013. And I get 2.89. And then I would take 14.00, subtract 2.89 from it, and I get 11.11. So either one of those methods will work. Oftentimes I actually ask for hydronium ion concentration as part of the problem, so that's why I did it that way, so you could have that example in your notes. If I don't ask for that, if I only ask for the pH and I don't have you calculate the concentration of everything, you could do it the second method where you calculate the pOH. Just as we did with our weak acids, we can describe the strength of our base using our equilibrium constant. So stronger bases will have larger KBs, right? Larger values for their equilibrium constant. Remember, our equilibrium constants are always products over reactants. The more it lies on the product side, right, the stronger it is. We can also calculate our pKb. Our pKb is going to be the negative log of Kb. And then again, because it's a negative log, it's going to be that inverse relationship. So stronger bases will have smaller pKbs, right? As your Kb gets larger, your pKb is going to get smaller because of that negative sign. So the stronger the base, right? As base strength increases, we're going to have larger Kbs and smaller pKbs. An example, we can look at ammonia. We just did that one, right? We said that the Kb is 1.8 times 10 to the negative fifth. And let's look at methylamine. Methylamine is going to be CH3, and I'm going to have a nitrogen, and then that nitrogen is going to be bonded to 2 hydrogen. So it's very similar to ammonia, it's just I'm replacing one of those hydrogen with a CH3 group. And its Kb is 4.6 times 10 to the negative fourth molar. If I wanted the Kb for both of those, or sorry, the pKb, I'm going to take the negative log. So I'm just typing that into my calculator here, negative log of 1.8 times 10 to the negative fifth. Comes out to be 4.74. And then I'm going to do a similar thing with methylamine. So the negative log of 4.6 times 10 to the negative fourth. My pKb is 3.34. So looking at these, ammonia is my weaker of the acids, right? Base is a weaker of the base. The stronger base is going to have the larger pKb. So 1.8 times 10 to the negative fifth is actually smaller than 4.6 times 10 to the negative fifth. So methylamine is the stronger base. And then if we look at the pKbs, it has the smaller value. So this is my stronger of the two bases, right? It has the larger value for Kb and the smaller value for pKb. There is a relationship between Ka and Kb. And the relationship is that if you multiply the two by each other, you actually get Kw. So Kw is equal to Ka multiplied by Kb. And then, of course, if we wanted to take the pKa's and the pKb and the pKw, right, I get that 14.00 is equal to pKa plus pKb. And that can be a useful relationship. Sometimes you'll be given a base and then you'll be given a Ka. It would be the Ka of the conjugate acid. And if you need to determine the pH of that base, then you can use this expression to figure out the Kb. And we can do an example like that. It's probably good to do another example. So let's calculate the pH, and we'll just do pH this time, of a 0.200 molar. And we're gonna make this just a tad more involved. Sodium cyanide solution. And I'll help you with this. The Ka of hydrocyanic acid is, I'm looking it up here, 4.9 times 10 to the negative 10th. And that's all the information we're going to be given. So I know kind of where we would start. I know that HCN and CN minus are conjugate acid base pairs, right? HCN is a weak acid. We know that because it's not one of our strong acids, but also I'm given a Ka for it. That's generally our clue. So since I'm given a Ka for HCN, I know that that's a weak acid. CN minus is its conjugate base. So I know I have a basic solution, right? I'm given a concentration of a conjugate base, so I know that it's basic. The reason I know to separate sodium from cyanide is I know that sodium, right, if I have sodium and is an ionic compound, I can look at my solubility rules. I know it's completely dissociated, right? And that just goes back to last semester, to 150 or 151, whenever you had it. If I have a group 1A cation in an ionic compound and I put it in water, it's always going to separate. If I was to write my ionic and net ionic equation, sodium is probably just going to go away. And we'll talk more about that towards the end of this chapter. But basically, if you have sodium or potassium or lithium, you can just really always ignore it. The reason I added it is if you were to go into lab, you can't just get a jar of cyanide ions. You can't have an ion without its corresponding, right, oppositely charged ion. So I can't get a jar of sodium ions. I would have to get sodium chloride or some sort of negatively charged ion with it. Likewise, I can't just have cyanide. I would have to have some sort of positively charged ion with it. So by writing sodium cyanide is just a more accurate version of the problem. But we're going to ignore sodium. We know our solubility rules. We know it's completely dissociated. I'm not going to care about it. It's inert. So just ignore sodium. So what that means is I'm going to write my base dissociation equilibrium reaction using cyanide as my base. We're going to react it with water. I'm going to produce my conjugate acid plus my conjugate base. We're going to set up our ice table. So 0.200 molar, don't care about water, 0 and 0. Lose some unknown amount called x, gain it to the product side. All of them are 1x because I have coefficients of 1. And then at equilibrium, what I started out with, minus what I lost. And then on the product side, what I started out with, which was 0, plus what I gained. And then, because this is a base dissociation equilibrium equation, I need to set it equal to Kb, not Ka. However, I'm given Ka. We're going to determine Kb, though. We can calculate it using this expression. So we need, this is kind of our problem here, we need Kb, right? Cn minus is a base. we wrote our base dissociation equilibrium equation. So to get that, I'm going to take Kw. I'm going to divide Ka, which was provided with the problem, into it. And that's going to give me Kb. And I got 2.0 times 10 to the negative fifth. It is small, right? It's less than 10 to the negative third, so we're going to use that assumption again, that 0.200 minus x is about equal to 0.200. So when I set up my equilibrium constant expression, instead of writing this in there, I'm just going to write the 0.200. Okay, I think we can solve our problem now. So Kb is going to be equal to the concentration of hydrocyanic acid, which is x, multiplied by the concentration of hydroxide ion, which is x, so x squared, over the concentration of cyanide ions. We are using that assumption, so I'm just going to put in 0.200. I'm going to solve for x, so I'm grabbing my calculator. And I'm going to double check my work. And I got 0.0020. Right, I do want two significant digits. My calculator just comes out to be 0.002, but remember our calculators don't know significant digits. I have 2 here, I have 3 here, so I want 2 in my answer. And then we need to remember, right, what we're trying to get to is our pH. I need to remember that X in this case is my hydronium ion concentration. It's also my hydrocyanic acid concentration, but I don't need that to determine pH. So since I'm writing it equal to something that's got brackets around it, I'm going to throw those units on there. So I'm going to use the POH method. Since I'm not asked to solve for concentrations, I'm only asked to solve for pH. I find this way to be easier, but again, you can do it whatever method you prefer. So I'm going to take the negative log, and I'm going to get 2.70. In my calculator, it comes out to 2.69897 or so. Ooh, I actually did that wrong. No, I did it right. Sorry. Sig fig rule. I'm talking to myself here. I do want to have 2 digits after the decimal point. POH is a log value, and that would end me here. But because this is an 8, it's going to round that 9 up to a 10. So instead of 2.69, I get 2.70. And then to get my pH, 11.30 would be my pH.